In today's lecture, I will discuss concurrent and parallel forces, and I will apply those concepts to the concept of equilibrium of forces and torques. Let's begin the discussion with the definition of concurrent forces. So concurrent forces are those forces that are applied to or act at the same point as in the figure shown below. When two or more forces act at the same point, the resultant force is the sum of the forces applied at that point. And the resultant force is the single force that has the same effect as two or more forces acting together. So in this figure here, we have a boat that's being pulled upstream by two people pulling on two ropes. So each person applies a force along their own rope. And so the force is being moved by those two forces. However, the resultant force of those two forces, which is labeled with R here in the figure, is the force that has the same effect as those two individual forces. So if that resultant force was the only force acting on the boat would be moving exactly the same way as if there were these two forces acting on the boat. So for any number of forces that act on an object, we can replace them with their resultant force, which is calculated by adding those forces up. And so the object will then move the same way under the action of that resultant force. For the purposes of this lecture, however, I'm not going to discuss situations where the forces acting on an object form some angles between them, such as in the figure below here. What we are going to consider would be forces that are applied parallel to each other on an object. That will simplify the discussion, but it's going to be sufficient enough to illustrate the points and explain the principles that I want to discuss today. Let's talk about equilibrium of forces. So equilibrium is defined as the state of a body in which there is no change in motion. So a body is in equilibrium when the net force acting on that body is equal to zero, which means that the body may be under the action of several forces, but when all these forces are added together, the net result is zero, as if no force is acting on the body. So that means that the body is not accelerating, and it is either at rest or it is moving with constant velocity. Remember, constant velocity means that the direction of motion and the speed with which the body is moving aren't changing. Therefore, the body is not accelerating. So the study of objects in equilibrium is called statics. And statics is an important branch of engineering, and it is used, the concepts in statics are used in the building industry, building bridges, building structures, and so on and so forth. The forces applied to an object in one dimension act in the same direction or in opposite directions. And so for the net force to be zero, the forces in one direction must equal the net force in the sum of forces in one direction must be equal to the sum of forces in the opposite direction. And so symbolically, this could be written as the sum of forces in the positive direction must be equal to the sum of forces in the negative direction. Which direction is positive and which is negative is irrelevant. All that matters is that all forces directed in one direction added together must be equal to all forces directed in the opposite direction added together. So typically when we are talking about positive and negative directions, we consider to the right to be a positive direction, to the left to be a negative direction, and then up, vertically up is positive direction, vertically down is negative direction. This is a common accepted convention for directions, but all you need to really consider is that all forces in one direction added together must be equal to all forces in the opposite direction added together. So to illustrate this idea, consider this schematic representation of a bridge. So this is a bridge. Alright, so the bridge itself has mass and therefore it has weight. Again, weight was the force with which the gravity of Earth is pulling on the mass of an object. And so the weight of the bridge is exactly in the middle of the bridge, and it is pointing down towards the ground. Okay, and then the two ends of the bridge are supported by the banks here. And so, since the weight of the bridge is pulling down, the banks are going to apply normal force at each end of the bridge. And so now you can see from the picture here that all forces are parallel to each other. But we have two forces that point in one direction, up. Those are the support forces. And one force that points in opposite direction, down. That is the weight of the bridge. And so the bridge is in equilibrium. It is not moving. It's at rest. Which means that the sum of the forces at the supports is equal to the weight of the bridge. So let's label those. So the two support forces are equal to each other because the bridge, we will assume, is uniform. The mass is distributed evenly along the bridge. And so those two forces are equal, but they both point in positive direction. So let's label these with F plus. And then the weight of the bridge points down. So let's say that's the negative direction, so F minus. And then so the condition for equilibrium in one dimension simply states that F minus is equal to F plus plus F plus. And because of that, again, this bridge is not moving. So no matter how many forces are present in the particular example or problem or situation, if the sum of all forces that act in one direction is equal to the sum of all forces acting in the opposite direction, then this object is in equilibrium. And we can also reverse the statement and say that if an object is in equilibrium, that means that the sum of all forces acting in one direction must be equal to the sum of all forces acting in the opposite direction. Let's apply the principle of equilibrium to the following example. So Harry and Mary, Bill and Jill are playing a game of tug of war. Harry and Mary are pulling to the left with 100 newtons and a 75 newton forces respectively. If Bill is pulling to the right with 115 newtons, how much force is Jill pulling with so that there is equilibrium? So let's sketch the situation and let's see how we deal with this problem. So here is our rope. That's the middle of the rope. Now let's draw the forces with which the participants are pulling on the rope. So Harry is pulling with 100 newtons of force. Mary is pulling with 75 newtons of force. Then we have Bill pulling to the right with 115 newtons. That is Bill. And we want to find the force with which Jill is pulling to the right. Okay, so since this is equilibrium, that means that the sum of all forces that pulling in one direction must be equal to the sum of all forces pulling in the opposite direction, which means that the sum of the forces with which Harry and Mary are pulling to the left must be equal to the sum of forces with which Bill and Jill are pulling to the right. So let's write this down. And I'm going to use the first letters of their names as the names of the forces. Okay, so I know all the forces except for the force that Jill is pulling with. So I'm going to replace those values in this equation. And so we have that 100 newtons plus 75 newtons is equal to 115 newtons plus the force with which Jill is pulling on the rope. So from here, moving the 115 newtons on the left side, I get that the force with which Jill is pulling on the rope is equal to 100 newtons plus 75 newtons minus 115 newtons, and this is equal to 60 newtons, and that is the answer. The second important quantity that is associated with equilibrium is torque. Torque is produced when a force is applied to produce a rotation, as for example when a wrench is used to turn a bolt or a claw hammer is used to pull a nail from wood. Torque is the tendency to produce change in rotational motion. The torque developed depends on two factors: the amount of force applied and how far from the point of rotation is the force applied. The expression for torque is given by this equation. The torque tau is equal to the product of the applied force F and the distance from the point of rotation, which is called length of torque arm, ST, length of torque arm. For simplicity, I will refer to the length of torque arm simply as torque arm. And so what are the units for torque? Well, in the metric system, those will be the product. That will be the product of the units of force and length. So that will be Newton meters. And in the imperial system, we have pound feet. Here is an illustration of the dependence of torque on the force that's applied and the distance from the point of rotation. So here we have a wrench here that's used to tighten a bolt. And so the point of rotation or the axis of rotation is the center of the bolt. So for the force that's applied here in those three situations, which is constant, the greatest torque is generated when the distance from the axis of rotation is the greatest. And so when there is a limitation on the force that can be applied to produce torque, the solution to increasing the torque would be to increase the torque arm. And for example, if you are changing a tire and the lugs are really tight and it's really hard to loosen them up by hand with the wrench that you have at hand, you can use a pipe to make the torque arm much longer, and for the same amount of force that you could apply, you are going to increase the torque significantly, and that will allow you to loosen the lugs. Now, if the torque arm is fixed in length, there is no way to increase that, then in order to increase the torque, obviously, the force that's applied must be increased. Apart from the magnitude of the force and how far from the axis of rotation it's applied, there is also one more consideration that determines the magnitude of the torque that's generated, and that is the direction in which the force is applied with respect to the axis of rotation. So in the example shown in the figure, we have the bolt, we have the wrench here, and I want to tighten the bolt. So if I apply force straight towards the axis of rotation, this force will not generate any torque because it is directed along the line that passes through the axis of rotation, which means that there is no effective torque arm here. And you know that from experience. Let's say you want to open or close a door and you push straight against the hinges, in the direction of the hinges. The door is never going to move. Another possibility for application of force here would be to have the force at some angle, like this. Well, now there is going to be some torque generated. There will be rotation, but it is not going to correspond to the entire force. Not all of that force is going to go towards rotation. Why is that? Because there is parts of the force, a portion of the force is essentially directed towards the axis of rotation, and then what's left is directed perpendicular, and therefore only that portion here will generate torque. So if you are able to measure the torque generated by that much force versus the entire force acting in perpendicular to the wrench, you would find that in the second case you are generating more torque. So not only the magnitude of the force and the distance from the axis of rotation, so the length of the torque arm matters, but also how is the force oriented with respect to the axis of rotation matters for the generated torque, for the magnitude of the generated torque. Here we have a different situation where torque is generated. So we have a bicycle sprocket here with pedals, and so the foot is pushing down on the pedal, so it's applying downward force, and the effective torque arm here is the distance from where the force is applied to the axis of rotation. So when is this torque here maximum? When do we have the biggest torque? Well, the biggest torque is generated only when the pedal reaches a position perpendicular to the applied force. So as you can see here, the pedal is not perpendicular to the applied force. However, in this particular situation, as the pedal turns, now the pedal is perpendicular to the applied force. In this case, the force is the same, but the distance from where the force is applied to the axis of rotation is bigger compared to the previous position of the pedal. And so the generated torque in the second situation here is larger than the generated torque in the first situation here. So the maximum torque as the pedals turn is generated when the pedals are perpendicular to the applied force, and the minimum torque is generated when the pedals are parallel to the applied force. So that would be the position where the pedal is vertically up here. Let's look at the following example of application of the formula for torque. An engine bolt is torqued at 30 Newton meters. If the length of the wrench is 29 centimeters, what force is applied on the wrench? So we know the applied torque, which is 30 Newton meters. We know the length of the wrench, which is essentially the torque arm, 29 centimeters. We are looking for the force. So by definition, torque is equal to the product of force and torque arm. And since I'm trying to find what the force was, I need to rearrange this formula to solve for the force. And so F is equal to the torque tau divided by the torque arm ST. Now I'm ready to substitute the values in this formula and solve for the force. So that is 30 Newton meters divided by 29 centimeters. And now I see that there is a problem here. So the torque is in units of Newton meters, but the torque arm is in units of centimeters. So the units of length in the torque and the units of length in the torque arm are not the same. So therefore, before I can calculate the answer to this question, I must make the units the same. And so I will convert the length of the torque arm from centimeters to meters. And so that becomes 30 Newton meters divided by 0.29 meters. And now the units of meters cancel out, and the force is equal to 103.4 newtons. So it is important to remember that you must have compatibility of units when you're calculating torque. Since torque is measured in Newton meters in the metric system, that means that the torque arm must be also in meters. You cannot have it in other units. If you do not do the conversion, your answer will be wrong. Now that we have discussed what resultant force is, what parallel forces are, and what torque is, we are ready to discuss conditions for equilibrium. So the first condition of equilibrium is related to the concept of parallel forces. So let's look at this situation. So we have a painter who is standing on a plank which is supported by a scaffold. And the schematic representation of this situation is shown here on the right. So here is the plank, the painter is standing on the plank, and so the weight of the painter is pushing down on the plank. And then as a result, the two supports apply upward force on the plank, and the whole assembly is in equilibrium. There is no motion. So that means that the weight of the painter pointing down is balanced by the sum of those two forces at the supports. You also will notice that the support that is closer to the painter, so that would be the left support here, exerts larger force on the plank compared to the right support, which is further from the painter. And that makes sense, since the left support must support more of the weight that is placed on the plank, and the right support must support less less of the weight. So the weight of the painter and the two forces at the supports are all parallel to each other. So these are parallel forces. And since this assembly is not moving, it is in equilibrium. That means that the sum of the two forces at the supports is equal to the sum of it's equal to the weight pushing down. So if I wanted to write this relationship between the forces in an equation form, it would read that the weight, which is pushing down, is equal to the sum of the forces at the two supports, which are pushing up. And so I can also rearrange the terms to look like that. F1 plus F2 plus minus Fw is equal to 0. And so the sum of all parallel forces now is equal to 0. Here I have accounted for direction as well. If you remember, I stated on a previous slide that all forces that point up are considered positive, so F1 and F2 point up, so I took them with positive signs. And then all forces that point down are considered negative, so the weight of this painter is pushing down, so therefore I have it here with a negative sign. And so when you add the three forces together, the net result is 0. 0 net force acts on the plank here, and therefore the plank is not moving, it is in equilibrium. And so essentially this is an example of the statement that is known as the first condition of equilibrium, which involves parallel forces. So let's put it on the slide. The first condition of equilibrium states that the sum of all parallel forces on a body in equilibrium must be 0. So no matter how many forces act on the body, the sum of all those forces, and they must be parallel, must be equal to 0 if the body is in equilibrium. So if a body is in equilibrium, and we know that for sure, that means that the sum of all parallel forces acting on that body is 0. And of course, we can also reverse the statement. If the sum of all parallel forces acting on a body is 0, that means that this body is in equilibrium. The second condition of equilibrium is related to equilibrium of torques. So imagine that for the painter that's standing on this plank, which is supported by the scaffold, for some reason, let's say the plank slips sideways and then the right support no longer supports it. What's going to happen? Well, the painter is going to fall because the plank will start to rotate about an axis that passes through the left support. So schematically, the situation looks like the right drawing here. So we have the force applied by the left support on the plank. The weight of the painter is pushing down. There is no force applied at the right support on the plank, and so as a result the plank is going to rotate about the left support. So the plank is no longer in equilibrium, and then there is rotation involved now. So in this example, I'm dealing with two parallel forces, F1 and the weight of the painter, but those two forces are not equal to each other. And so you might say, well, because they're not equal to each other, that's why there is rotation. Okay, but I can also show you an example where the two parallel forces are equal to each other, opposite in direction, and there is rotation involved in that situation as well. So for example, imagine a meter stick that is fixed in the middle, so it cannot slide, it can only rotate. And I apply the same force F at each end in opposite directions. So those two forces are parallel to each other. equal to each other, so the sum of parallel forces is 0. But because of the fact that the meter stick is pinned in the middle, those two forces will cause the meter stick to rotate in counterclockwise direction. So there will be rotation. So that means that even if the sum of all parallel forces is equal to 0, that is not enough requirement for an object to be in equilibrium. There also must be a requirement for the torques of those forces that act on this object to be related in a certain way so that there is equilibrium. So what is that way in which those forces must be related? That is the essence of the second condition of equilibrium. So if you want the condition of no rotation to be satisfied, that means that there must be no unbalanced torques in the system. It means that all torques must cancel out. And so before I actually state the second condition of equilibrium in terms of torques, I also must introduce the concept of clockwise and counterclockwise torque. So let's quickly run through the nomenclature of clockwise and counterclockwise torque. So I have this meter stick that is fixed in the middle to rotate about that point, and 4 forces applied to that meter stick. We have force F1, F2, F3, and F4. So let's determine what type of torque does each force generate. So the force F1 will rotate the meter stick in clockwise direction. So therefore, F1 is going to generate a clockwise torque. Then F2 also wants to rotate the stick in clockwise direction. So F2 also generates clockwise torque. F3 wants to rotate the meter stick in counterclockwise direction. So the force F3 will generate counterclockwise torque. And finally, F4 wants to rotate the meter stick in clockwise direction, so therefore F4 generates clockwise torque. So notice that these directions of rotation are determined by the position of the axis of rotation. In this case, that is in the middle of the meter stick. If I would select the axis of rotation to be at the left end of the stick, right here, then the force F1 will produce no torque because it's applied at the axis of rotation. There is no torque arm with respect to that. And then the other 3 forces, F2, F4, and F3, all will be producing clockwise torques because with respect to this new selected axis of rotation, all of these forces tend to rotate in clockwise direction. Now, if I selected the axis of rotation at the right end of the meter stick right here, then the force F2 produces no torque because it's applied at the axis of rotation. F1 produces clockwise torque, and F3 and F4 produce counterclockwise torque. So when we are dealing with a problem where we have several forces acting on an object, the direction of the torque that each force produces would depend on the selection of axis of rotation. And the selection of axis of rotation, unless specifically specified in the problem, can be random. And we only then need to be careful how are the torques produced by the forces in the problem rotating that object. So I will explain that when I show an example calculation. But now we are ready to put the statement of the second condition of equilibrium on the slide. And so the second condition of equilibrium simply states that the sum of all clockwise torques on a body in equilibrium must be equal to the sum of the counterclockwise torques on the body in equilibrium, and that is about any point of rotation. So no matter how I select my point of rotation on a body, the sum of all clockwise torques must be equal to the sum of all counterclockwise torques. And this is simply the statement of the second condition of equilibrium. Another way to state this is that simply there is no net torque acting on the system. The net torque is zero. That's another way to state the second condition of equilibrium. Now, combining the two equilibrium conditions for parallel forces and for torques leads to what is known as total equilibrium. Total equilibrium is the state of a body in which there is no change in its motion. That means that the sum of all parallel forces is equal to zero, and also that the sum of all clockwise torques is equal to the sum of all counterclockwise torques. So both equilibrium conditions must be satisfied at the same time to say that an object is in total equilibrium. And we are going to use that definition to solve some example problems using parallel forces equilibrium and torques equilibrium. The first example is about balancing a lever. So a 2 kilogram mass is placed 12 meters from the fulcrum of a lever. The question is, where should a 13 kilogram mass be placed to balance the lever? So here is a sketch of the problem. This is the lever. So it's a beam. This is the fulcrum. The 2 kilogram mass is placed 12 meters from the fulcrum, and then the 13 kilogram mass is placed an unknown distance from the fulcrum, and the question is, what is that unknown distance so that the lever is balanced? So the question here is, what does it mean for the lever to be balanced? Well, that means that the lever is not swinging about the fulcrum. There is no rotation about the fulcrum. So rotation is caused by torques. So therefore, this problem is about setting the torques due to the 2 kilogram mass and the 13 kilogram mass equal to each other. So then that means that I must determine the forces that are acting in this problem. There are two forces, and those forces are the weight of the two masses. So let's call the weight of the 2 kilogram mass Fw1 and the weight of the 13 kilogram mass Fw2. And so we want the torques due to those two weights to be equal to each other. So we want the torque of Fw1, let's call it torque 1, to be equal to the torque of Fw2, torque 2. So now let's write down the two torques explicitly. So the torque of the weight of the 2 kilogram mass is equal to the product of that weight and the torque arm, let's call it ST1, and on the other hand that has to be equal to the weight of the 13 kilogram mass Fw2 times X, and X is the torque arm for that weight. So the weight of the 2 kilogram mass is 2 kilograms times 9.8 meters per second squared, so that is 19.6 newtons. And the weight of the 13 kilogram mass is 127.4 newtons. And the torque arm of the weight of the 2 kilogram mass, ST1, is 12 meters. Now let's substitute all of those in the equality of the two torques, and let's calculate the result. Substituting in the above formula gives us 19.6 newtons times 12 meters is equal to 127.4 newtons times X, from where X is equal to 19.6 newtons times 12 meters divided by 127.4 newtons. The final result is that x is equal to 1.85 meters. So here in this problem I used the second condition for equilibrium, which was that the sum of all clockwise torques is equal to the sum of all counterclockwise torques. In this particular example, the clockwise torques, there is only one of those, and that is the torque due to the weight of the 13 kilogram mass that tends to rotate the lever in clockwise direction. And there is only one counterclockwise torque, and that is the torque due to the 2 kilogram mass, which tends to, that is the weight of the 2 kilogram mass, which tends to rotate the lever in counterclockwise direction. And so the two torques are equal to each other. So this here is the second equilibrium condition. Let's do one more example. This time I will use both conditions for equilibrium to solve this problem. So we have a plank, and a person is standing on the plank closer to the left support. So the person has a weight of 180 pounds and it's standing 3 feet from the left support and 6 feet from the right support. And the question in this example is, what are the magnitudes of the two reaction forces F1 and F2 at the left and right support? So what are those two forces equal to? That is the question. So clearly this configuration here is in equilibrium. There is no motion whatsoever. The person is standing still. The two supports are holding the plank in place. There is no rotation. There is no linear motion. Now we have three forces that are present in this configuration. We have the two support forces pushing up, and then we have the weight of the person pushing down. So that means that the weight of the person is balanced by the two forces at the supports. So this is the first condition of equilibrium. So 180 pounds is equal to F1 plus F2. And that is the first condition of equilibrium. Now we also, it's impossible to solve the problem because I only have one known quantity right now, and that is the weight of the person, and I know I have the two unknowns, which are the two forces at the supports. So if I wanted to find those, I need one more relationship that will help me do that. And so this relationship will come from the second condition of equilibrium, which is about torques. So how do I apply that? Well, first of all, I must select a point of rotation here. And I can do that selection in any way I want, but the smart selection would be to select a point of rotation at a point where a force is acting. So when that happens, this particular force will have no torque with respect to that point of rotation. And so I will select my point of rotation to be at the left support, right here. So I'm going to calculate all torques with respect to that point of rotation. So just to clarify, even though I'm calculating torques, this plank is not rotating really. It is not rotating, but in order to apply the second condition of equilibrium, I must calculate torques, and therefore I'm selecting a point of rotation, and for convenience, I'm taking it to be at the left support. So when that happens, force F1 has no torque. because it acts at the point of rotation. So then there is only two torques left to consider. The torque of the weight of the guy, which tends to rotate the plank in clockwise direction, so that would be a clockwise torque. And the torque due to force F2, which will tend to rotate the plank in counterclockwise direction, so counterclockwise torque. And so the second condition of equilibrium says that the sum of all clockwise torques is equal to the sum of all counterclockwise torques. So we have one clockwise torque and one counterclockwise torque, so therefore the torque of the weight of the guy is equal to the torque of force F2. The torque of the weight of the person is equal to the torque of force F2. Or if I replace those with the product of force and torque arm distance, we have 180 pounds, the weight of the guy, times 3 feet from the left support, is equal to the force F2 times 9 feet from the left support. So remember, force F2 is 6 feet from the person, but then there is 3 more feet to the left support, so the total length of the plank here is 9 feet, and that's the distance from F2 to the selected point of rotation. Alright, so now I just need to calculate the result for F. So F2 is equal to 180 pounds times 3 feet divided by 9 feet. The units of length cancel out, and the result is 60 pounds. So I've got that result by applying the second condition of equilibrium. So now how do I find the other force, F1? Well, I go back to the first condition of equilibrium and substitute F2 with the value that I just found. So we have that 180 pounds is equal to F1 plus 60 pounds. Well, from here, F1 is equal to 180 pounds minus 60 pounds. And that is equal to 120 pounds. So this is a great example to show how a problem where we have two unknown quantities, which is a problem about equilibrium, can be solved by using the two conditions of equilibrium: equilibrium of parallel forces and equilibrium of torques. So how can this problem be modified? Well, for example, there can be a situation where there is another person on the plank or a load of materials on the plank, so that will bring another weight force pushing down. That will only change the number of forces and number of torques involved in the two conditions of equilibrium when you record them to solve the problem, but it will not change the basic principle or the fundamental principle behind solving those types of problems. So the solution will be essentially the same, but extra terms will be added where necessary to account for another possible force of weight on the plank. So this concludes the lecture on concurrent and parallel forces. And you guys will practice those concepts when you do the worksheet in class.